Good afternoon, everyone. Oh, this mic is terrible. Today we have Professor Paolo Bestagini. He's a professor in Politecnico di Milano. He's a very good friend of mine. We've met in 2012.
I think so.
Yeah, this is the second time he comes to Brazil, and perhaps some of you were here last year when he gave us a talk about his research topics. And I'm glad to have him again this year, and we are already discussing, Paolo, Simone and I, to have again next year and so on and so forth. Of course, I'll go there too. So thank you very much for being here today. Paolo is going to talk to us about some of the image and sound research that they have been carrying out in the Politecnico di Milano. We have some of these works are being done in collaboration, right? And some others he has been doing with partners in the US and in Europe. So thank you very much, and the stage is yours.
Thank you. Thank you again for inviting me and giving me this opportunity. I'm Paolo Bestagini from Politecnico di Milano, as Professor Anderson was telling you. Before going deeper into the technical parts of the presentation, I'd like to spend a couple of words about the research group I'm working with at Politecnico di Milano and Politecnico di Milano itself, for those of you who might not know the place in Italy. So this is a view of Politecnico di Milano, the main campus. It's a leading university in Italy since 1863. The peculiarity of Politecnico di Milano compared to other Italian universities is that we only teach in three areas. Engineering, design, and architecture. So there are no other area investigated there. This is a picture of the historical building of the main campus back in 1930. It might be not so impressive to you right now, but if you think about that for Italy, back then, already having the idea of a campus like this was something amazing, actually. Going back to the campus, Politecnico di Milano, despite the name, is not just based in Milan. Actually, it's based in a multiple city in the northern part of Italy, the most of which are in Lombardia, which is the region to which Milan belong, but not only Lombardia. And actually on this map you can see we have part of the campus displaced in Como, in Lecco, in Cremona, in Mantova, but also Piacenza, which is just outside of the region. To give you an idea of some numbers, how many students we have, how many faculties we have in the various areas, I have these slides here. So for architecture, if you think just about that, we have almost 300 in terms of faculties and almost 7,000 students. If you think about design, it's 94 faculties and 3,500 students, whereas for engineering, we are almost 1,000 faculties and more than 27,000 students in Milan. What about the spread of Italian architects, designers, and engineers according to Politecnico di Milano origin? Well, on this map you can see that the 21% of the architects in Italy that works in Italy actually are graduated from Politecnico di Milano. The 16% of engineers in Italy comes from Politecnico di Milano, and the 42% of designers in Italy graduated at Politecnico di Milano. Now, if we zoom in Politecnico di Milano, of course, there are many departments. So let me spend a couple of words about the department I'm working with. The Dipartimento di Elettronica, Informazione, Bioingegneria. Actually, there has been quite a war whether we wanted to translate this in English or not. So sometimes someone translates into English, sometimes it is left in Italian. I think that here is probably very easy to understand the meaning also in Italian, but it's the Department of Electronics, Information and Bioengineering, by the way. The history of the department is pretty long as well. So it was born in 1886, and the name was different actually. It was just Department of Electrical Engineering, and through years the name of the department changes. And since 2013, we are DEIB, D-E-I-B, Dipartimento di Elettronica, Informazione, Bioingegneria, which is the name that we actually have nowadays. In terms of people distribution within the department, we have around 200 research assistants, 14 CNR, which are other researchers collaborating with Politecnico, 60-something technical and administration staff, 59 assistant professors, 72 full professor, almost 300 PhD students at the department, and more than 100 associate professors just there. In terms of revenues, actually, these are increasing year by year. So here I was just reporting as a quick screenshot, which are the revenues for the department, just the dev department, from 2014 to 2017, and you can see that actually the amount of funding that we can get from different sources is getting higher and higher, which to me means that we are hopefully working well. Also in terms of patents, I can show you that we have tens of patents published every year, and which are the research areas. There actually are multiple the research areas that are being investigated at Politecnico at that time. So from system and control to bioengineering, electrical engineering stuff, electrical branch, computer science, and finally telecommunication engineering, which is actually the branch I'm coming from. Which are, just to give you the last numbers, the last figures about the department, how many labs we have and which one they are. So we have 9 laboratories just for bioengineering people, 17 managed by computer science researchers, 5 by electrical engineering people, 8 for electronics, and 10 laboratories concerned with telecommunication research. One of these laboratories is actually the lab in which I'm working, so it's the Image and Sound Processing Lab, ISPL. Who we are? We are 5 faculties in between full, associated, and assistant professor. Right now we have 4 postdocs working with us, 8 PhD students, and other, counting research assistant, visiting people. You might probably know Pedro, who's visiting us right now from University of Campinas. And these numbers actually varies a lot, so this is just a screenshot of today. But if we count visiting person, actually this changes like a lot in time. Research areas in which we are involved, actually there are many. From audio processing to image processing to video processing, we can split them mainly into 4 areas. So in terms of image and video processing, we have some ongoing project with DARPA. We had some ongoing project funded by the European Commission. We have some ongoing research on space-time processing for audio. We also analyze geophysical data, so we have people working specifically on seismic inversion and the analysis of geophysical imaging, and there are also students working on music information retrieval stuff. Here a quick overview of the main topics we're dealing with. So in terms of music information retrieval, for example, we're working with similarity between music tracks. We're working with music recommendation systems. In terms of space-time audio processing, we have ongoing research on acoustic source localization, on rendering of acoustic scenes. We are working also on the detection of hazardous events from microphone recordings. And there are also people working on non-linear audio processing, specifically dealing with sound synthesis and virtual analog, so they're trying to recreate algorithms to generate sounds according to maybe some old circuits that were used in some old instruments. I was telling you we work on geophysical images, so we have seismic image processing research going on with an Italian company working on oil. We have some research on industrial application concerning computer vision and digital image processing, for example, for food quality assessment. We are working also on 3D processing, and right now we have 2 projects going on, one for automatic docking of boats into harbors using cameras and 3D view of the scene, and also the analysis of doctors working with patients to see whether actually they are keeping the correct position or they might be in some dangerous position for their working condition. And last but not the least, multimedia forensics, which is the branch I'm mainly involved. Here we're working on tampering detection for video and images. We are developing deep learning methods for forensic researches, and I highlighted here the works that we are doing on device attribution, because actually today my talk is going to be mostly about device attribution. So, thank you for the patience for this, and let's now get to the technical part of my talk. What I want to talk to you today about is image and video source attribution in multimedia forensics. So, my idea is to give you a quick overview of which kind of algorithms have been developed in the literature and which kind of algorithms we are working on nowadays for this topic. Why? Well, I think all of you are convinced that images are part of our daily life. We take lots of images and pictures and photographs with our smartphone. We have cheap cameras. We can share those images online. We have social networks that we use like a lot. We can even share pictures with apps and use apps on our devices and smartphones to modify these pictures before sharing. And that's great for sure. But not everyone is using pictures just for this. So there are risks associated to the use of photographs and images and pictures. Photographs can be used really with malicious intent by many people. Just a few examples here. You can use picture to force opinion formation by spreading fake news, because you know a picture is worth 1,000 words. So when you associate a picture with a post of yours on a social network or a newspaper, you are enforcing somehow some ideas. But if you edited those pictures or if you use wrong picture for the wrong cause, you might really misbehave and create very, very bad situations. So for sure, nowadays there is a need of linking the pictures that are shared to the acquisition devices that were used to show this picture. Why? Why do we need to link a picture to the device? What is this giving to us in terms of information that we can exploit to fight this misbehavior? Well, let me give you some examples. One is the following. Let's suppose there is an anonymous, unknown, fake Facebook user that is posting some offensive or illegal material. You don't know who he is. But you know there are lots of other Facebook users, of course, and they also post pictures. What I'm going to show you that you can do is, okay, you can download pictures from all of the other users that are maybe suspicious. From these pictures, you can build a sort of fingerprint of the camera used by the users, and then you can link the pictures linked on the picture published on the fake account to some other user. So you might understand who the user was. Or you are analyzing a picture like the one to your left. Like the one in the middle. It might be fake, it might be original, you don't know, but if you can split the image into several blocks, and you can link each block of this image to a specific device, like it's done here, you link the two blocks highlighted in green to a specific smartphone, and you understand that the other blocks come from another smartphone, well, you can understand that that picture was modified by splicing together two different images. So, just linking part of pictures to devices might help you in this sense. And you can do the same for videos. Let's suppose you have a huge video, very long video. You might analyze it and understand that, okay, the first 400 frames have been acquired with one device. Then you have some other frames that have been acquired with a second device. And then the last amount of frames were acquired with a third device. So just by analyzing the video and being able to link the video frames to specific devices, you can understand that the video is a compilation, that the video was spliced in time. It's not an original sequence just took by a single camera. Maybe you're analyzing some closed camera TV recordings, and you might understand that that recording was tampered with. Or being able to link images to devices might also be helpful in terms of phylogenetic research that are being developed here at Unica. Let's suppose you are in this situation, you have a scene, and you have three different pictures of this scene, like the two on the left and the one on the right. You, in principle, might confuse them as all edited versions of the same pictures, but if you're able to understand that the two photographs rounded in orange come from one specific device, and the one rounded in green and blue comes from a different device, you can understand that actually those are not all images coming from the same root image. The first two images are actually near duplicates, they are edited versions from the same picture. The other image comes from another device. So if you're building phylogenetic trees of images, you might use this technique to separate images according to the device and separate different trees if you're working with phylogenetic forests, as Professor Anderson is doing in these many years of research on this topic. So, if you are convinced that being able to link an image to a device might be helpful, let's now formally formulate the problem, and let's see how we can do that. So, let's start from the problem. Source attribution. We have a picture, we want to understand where does this picture come from which device. This is everything and nothing if you think about that. I mean, it's a very general problem formulation. It tells us a lot, but it tells also us nothing because it's too broad. And actually, why? Because linking a picture to a device might be interpreted in many different ways, because there are many devices. We have scanners, we have camcorders, we have webcams, we have cameras, we have smartphones, and we have different models of the same smartphone, and we have different devices of the same model. So rather than treating source attribution problem as a whole, something that is typically done in the literature is to split the source attribution problem into different levels. So we have the first level is the so-called class attribution. You have a picture, you want to just understand which is the class of devices used to acquire that picture, which means you might want to understand whether the picture comes from a camera or from a scanner. This might help you in starting your investigation. The level 2 is the model or brand attribution. You have a picture, you know you're working with cameras now because you already split scanners and cameras beforehand, and now you want to understand, okay, which brand of camera or which model of camera was used to acquire this picture. But then you can go even further, and you can reach level 3 of device attribution, which is the real specific device attribution. You have a picture and you want to understand, okay, given that I have several devices of the same brand and model, which one of these was used to shot that pictures? And this, of course, it looks and it is much more difficult, but it's something that in the end you want to do. So let's go through these levels and let's see what you can do. Let's start from level 1. You have a picture, you just want to understand which is the class of the device that was used. There are some methods in the literature dealing with scanner versus camera pictures. So you have a picture, you want to understand, does it come from a scanner or from a camera? Here I'm listing a few references. Actually, you can find more, of course. One of the very well and very good methods that works very well for this kind of problem actually follows the pipeline reported in the slide. You have a picture, you denoise the image, you subtract the image to the denoised version, you obtain this noise residual, you extract some features that are related to how color channels of the image are correlated in between them, and then you feed this to a classifier, and you can understand whether this feature has been extracted from a picture that comes from a scanner or from a camera. There are other approaches as well, and another well-investigated problem into this level 1 of class attribution is, given a picture, can we understand whether it comes from a camera, so it's a natural picture, or it has been computer generated? And let me test you on this. If you have these 10 images here, can you just by visual inspection understand which are real photographs and which have been computer generated? I think also due to the projector, it's even harder. But even for me and even for you on a screen, this is a very hard test.
Is it the challenge, fake or real?
Is the challenge fake or real? Well, let me give you the answer because it's really, really challenging. CG stays for computer generated, the real stays for the camera pictures, and actually the first two, so the car and the coffee cup, were computer generated. Well, you might have guessed the coffee cup, but the car is really, really well done. The cork opener, the bottle opener, the third picture was real, whereas it might seem computer generated like the coffee cup. And you see that also for the other picture it's not so easy for us to understand which are real and which are not. But luckily, we have algorithms that help us in tackling this problem. How do they work? Well, there are many, again. So here I'm listing something and I'm just giving you a quick preview of how they can work. So for example, we have some working the extraction feature in the wavelet domain from the images and then feeding this feature to classifiers. Of course, as you might have guessed, there are methods out there working with convolutional neural network learning directly from the images whether they are real or not. But there are also some interesting methods that are specifically focusing on some peculiar cases. For example, if you're just talking about picture of faces of persons, you can try building a 3D model of the face, then try projecting the picture on this 3D model and look at the motion, the statistics of the movement of the person, of the face, if it's a video, or if you have images, you can try to see whether the picture really can fit a 3D model or not, and this might help you in disambiguating real photographs from computer-generated ones. If you notice that the title of the slides I was using for this last topic I'm talking to you, I have used the classical approaches title. Why did I do that? Because these approaches have been developed through the years. Some of these approaches are still part of research, but why do I think that today is important to deal with this sort of research? Because today we have a new class of computer-generated images that are not simply generated by using computer vision and 3D modeling. We know that nowadays with convolutional neural network and generative adversarial networks, we can really obtain pictures that looks like natural, but they're not. This is a very classical example of a network developed by NVIDIA, where they show that they can generate pictures of faces, but none of this is real. No one in these pictures that looks like photograph, no one of this person actually exists. They have been just generated by machines. And you can understand that this might become a serious threat in the future, because if you can generate faces, if you can manipulate faces, if you can manipulate picture using artificial intelligence with such a high quality, you can undermine the credibility of news that you're spreading because you are modifying the pictures, or you can cyberbully people using this sort of pictures and modifying pictures of your colleagues and so on and so forth. So nowadays I think it's really, really important to be able, given a picture or given a video, to understand whether it is real or it has been computer generated with one of these techniques. And actually this is something that is being faced in terms of research in the literature, starting basically this year. Some interesting methods that have been developed for deepfake videos. Well, one specifically focused on eye blinking. One researcher noticed that on the previous generation of deepfakes videos, the faces were not blinking the eyes. Whereas, of course, any natural person, any real person, sometimes needs to close and open the eyes, otherwise they would be completely dry. So they developed a method to detect the eyes in the videos, and then to spot whether the eyes blink in time or not. And if you have a video of a person that never closes his eyes, well, that video is fake. This method was very nice, but I think after a few weeks, if not less than that, from the other part of the research community, those working on generating these fakes, they were able to generate videos that now open and close the eyes. So this method was rendered completely useless for the new generation of deepfakes videos. But fortunately, there are other techniques. There are some other methods that exploit LSTM, so long short-term memory network, to study the evolution in time of the frames of a video to understand whether it's real or it has been generated. There are methods extracting some deep features and classifying these deep features. And we also started working on this topic. And what are we doing at Politecnico on this? Well, we tried a different approach. As if you model the deepfake videos, well, the deepfake creators might change their algorithm. We asked ourselves, why don't we try modeling the real videos and detect the fake videos, the computer-generated ones, as not real? So we started actually from a very old idea that was already exploited for other forensic stuff, that was the use of Benford's law. Actually, if you have a picture, a natural picture, so you're not just taking random pictures of random pattern, but if you go outside, take a picture of nice landscape, picture with people, pictures of natural scenes, you can statistically observe that the pixels should follow some statistical distribution. Benford's law is one of these particular statistics that should be followed by the pixels of a natural image. So we tried training a classifier to understand whether a picture followed this Benford's law or not, because a computer-generated picture might not follow this law. They are not. No one is telling the generator of deepfakes to precisely follow this statistical law, whereas natural picture might. So we tried implementing this. And we tried this method on different datasets of natural images. We used the UC, DRACE, Dresden. There are 3 well-known forensic datasets of natural pictures. And we used GAN-generated images obtained with different implementation of different networks. Here are some of the examples of the GAN-generated images that we used. So some of you might be familiar with the cycle GAN turning apples into oranges, like in this picture, bottom left, and oranges into apple. We have the faces generated by the program at NVIDIA. We have pictures generated turning paintings into real images, and vice versa. We have pictures of zebras that are actually horses that are being turned into zebras by artificial intelligence method. And we try disambiguating. Given a picture, is it natural or has it been generated by a network? And results were pretty promising, actually. In this picture, I show you for each dataset, so for each class of pictures that we had, the accuracy that we had in detecting those pictures are natural or GAN-generated. So the first 3 columns here show that for the 3 datasets of natural images, we basically always get with an accuracy that higher than 95% that those pictures are natural. Whereas all of the other pictures are pictures belonging to GAN-generated datasets. And there, what can we observe? That actually for many of the datasets, like the faces, the apple to oranges, the orange turned into apples, zebras turning into horses turned into zebras, summer to winter, and so on and so forth, actually the method was pretty promising. We can detect that the picture was computer-generated with a very high probability, but we had some problem with a couple of datasets. To me, this is nice. Let me show you why. And let me show you, to do that, let me show you which are those datasets we are having trouble with. The first one is the dataset composed by pictures that are painting from the artist Monet turned into photographs. When we analyze this picture, photographs obtained by Monet painting...
This is with style transfer?
This was done with style transfer, yes. Here, our algorithm doesn't work very well. But to me it's nice because that method was specifically implemented to turn something into photographs. So probably the method also learned the statistical behavior of the pictures that we are exploiting. Another dataset on which we are not working that well is the photo enhancement dataset. Those are pictures that are actually real photographs that are being enhanced by a generative adversarial network algorithm. So actually these were pictures at the beginning, this has been enhanced, but probably the generator didn't change the statistic that much. So we cannot understand that they were real just by observing at this statistic, which means that there is still a lot of work to do in this sense. Let's now enter the level 2 of device attribution, which is brand of model. Now we have a picture. Now we know that the picture comes from a photograph, from a camera, let's say, and we are interested in understanding the model. Of course, this is very challenging. It's even more challenging than before if you think about that, because if I just show you these 2 groups of 3 pictures here, and can you understand that different pictures of the same object, of the same scene, come from different cameras? To some extent, yes, because you have cameras that are better than others, but just given a picture to understand the model that was used by visual inspection, of course, it's not that easy. You can do that algorithmically. Which is the key assumption behind that? Well, the key assumption is that every camera model from every different brand as a very specific acquisition pipeline. So of course there are some building blocks that are always in there to acquire a picture with a camera, and these are represented by this pipeline here in the slide. You have a scene, lights go through a lens, you probably have an anti-aliasing filter, the light rays pass through the color filter array and they hit a sensor, and then you have a demosaicing algorithm to recover the color of the image. You probably have several post-processing steps. You have a compression step to save the image into whatever compression format and whatever quality you're selecting on your device, and then you finally have the pictures. But all of these blocks can be different for different branded models of cameras. So the idea is we can exploit, we can study traces left by these small building blocks in the pipeline to understand which is the camera that was specifically used for acquiring a picture. In this sense, we have methods in the literature dealing with exploiting traces left by the lens itself. We know that lenses are not perfect, so they introduce some radial distortion. If you have a straight line, if I take pictures of these walls where there are lots of straight lines, and my camera doesn't have a perfect lens, the straight lines might be distorted while I'm taking the photographs. So, on one end, you might end up with distortions on your images, so straight lines are no more straight. On the other hand, you might use, your camera might use some correction algorithm that tries to make the lines straight again. Either way, or the lens or the algorithm that is used is leaving some processing trace on your image that you can exploit. Here I'm linking a couple of methods that actually try to estimate how curved are the lines that should be straight on a picture, and based on that they can understand which kind of lens, so which kind of device you were using. These are nice work, but what's the issue of one of such algorithms? Well, that on very high quality camera and DSLR cameras you can change the lens. So they can detect the lens, but you change the lens of your device, they cannot detect you anymore just because you changed the lens. So of course there are always some drawbacks in these sort of techniques. Other techniques that are very robust exploit traces left by the color filter array, which is in your acquisition pipeline. Now, what's the color filter array for those of you who are not familiar with this? To understand this, we have to understand how images are acquired by a single sensor camera. How does the sensor work? You can imagine that the sensor of your camera is a matrix composed by multiple cells. Each cell records how much light hit the cell. And the more the light, the brighter will be the pixel represented by that cell. So you have array light hitting with a very strong power one cell of the sensor. The corresponding pixel of your image will be white. You have one cell of your sensor that is not hit by light at all. The corresponding pixel on your image will be black. If you have a grayscale image, that's easy. If you have an average amount of light, it's neither white nor black, it's going to be of some gray level, the pixel corresponding to the cell. But how can you record information about the color? Well, the trick is to use the so-called color filter array, CFA. You superimpose like in the picture here, to your sensor, a very thin layer of color filters. So now each cell of your sensor only acquires information about green, or about red, or about blue color. Which means that you end up with a picture like the one on the bottom, where for each pixel you only know the amount of red, or green, or blue that belongs to that pixel. But how can you get the full color image at full resolution at the end? Well, you need to interpolate all of the red information that you have for all pixels. You need to interpolate all of the green information that you have for your pixel, and you need to interpolate also all the blue information that you have pixel by pixel. Then you can merge all of the three color channels together and obtain a full color image. But why is this interesting from a forensic point of view? Because different cameras might use different color filter arrays. So here I am reporting possible color filter arrays that might be used by different vendors. So if you have a picture and you can understand which color filter array was used to acquire that picture, you can understand which kind of camera was used. Another thing is different brands and different models of cameras has different firmwares, of course, and on the firmwares you have implemented different algorithms for interpolating the red, blue and green color information, which means that if you can understand which interpolation algorithm was used, you still can gather some information about the used device, the used brand or used model. And there are some methods doing this in the literature. What's the issue of these methods? Well, that not all cameras work with the color filter array. There exist cameras that exploit multiple sensors, like in the picture that I have here is an acquisition scheme of a camera that has 3 sensors. You have a prism in front of your lens. The prism separates the red, blue and green colors of the lights. Red light is diverted to a specific sensor that only acquires red information, then green light goes to another sensor, and the blue light goes to another sensor. Here you don't have the filter array, you don't need to interpolate anything. This method would not work.
Is it the Foveon camera?
Yeah. So, very robust methods, but they do not always work. And another issue that they have, they are strongly hindered by JPEG compression, because these interpolation traces are really, really subtle. You start compressing your images, like you upload your images on Facebook, you share your image through WhatsApp that is compressing the image more and more, you lose the possibility of detecting these interpolation traces. There are other techniques as well that are exploiting statistical traces left, that basically capture some statistics of the overall acquisition pipeline and not just one of the specific building blocks. One that is very, very famous and that works very, very well is to use the so-called rich features to capture pixel statistics and to link those to a camera model or brand. What you do, you have a picture, you apply some denoising step and you obtain a noise level from that picture. You then quantize even more and truncate this noise level, and then you start counting how many occurrences of series of pixels you have. Like how many times I observe that I have two neighboring pixels being 1 and 2. How many times I have the sequence of pixel 1, 3. How many times I have the sequence of pixels 0, 3. You count these for your image. This is a feature vector, this histogram counting how many occurrences that you have. You feed this feature vector to a classifier, and actually this so-called rich feature work really, really well. What's the issue is that in order to be informative enough, this rich feature vector, you need to compute it on quite large resolution images. If the image resolution is too small, you don't have enough statistics to build this vector, so it typically doesn't work well enough. But of course, those were all kind of model-based techniques, but we are in an era where data-driven approaches are taking the lead. And of course, also for this topic, we can find in the literatures many data-driven approaches. So we don't model anymore specific steps of the acquisition chain. What we do is we feed a learning algorithm with lots of labeled images, and we try to directly understand, to make a network, typically a convolutional neural network, understand how it can disambiguate pictures coming from different camera brand and model. What's the pro? One of the typical pro of these methods is that they typically work very, very well also with small patches, where the rich feature were not working well enough. And nowadays, the state-of-the-art accuracy is actually achieved using data-driven method rather than model-based method for this specific problem. What's the problem here? Which are the issues? If you have a big enough in terms of resolution picture, then the rich feature might work slightly better or on par. But you really need to have high resolution picture. If you have a small, low resolution picture or just a few patches, data-driven approaches work much better.
What do you call high resolution? How many meg?
5K by 5K or 2K by 2K.
So at least 2 megapixels.
Or 4. 4. Which nowadays is not impossible, of course, but if you are interested in analyzing just a small region of the image, like to detect splicing, that might be a problem. because maybe you have a very small object put inside another image and you want to detect
because
it.
2K by 2K is not a typical size for social networks, right? Normally they are smaller.
Also, when you send images by email, you can typically choose
Reduce.
low, medium, or high resolution, and so sometimes you compress them and you resample them to a lower resolution as well. Considering these data-driven approaches, what did we do at Politecnico? So let me show you quickly one of the methods that we implemented. We worked on this problem by proposing a neural network that actually allow us, given a picture, to understand which camera model was used, but also to understand which part of the image are used to achieve these results and to understand the camera model, what we call the reliability mask. Why? Because, as I'm going to show you, our network works patch by patch, but not all of the patches are informative enough. So how this pipeline works? Well, we have a feature extractor, which is a convolutional neural network. Actually, we used a fairly simple LeNet-inspired architecture with convolutional layers, GLU, and some max pooling, nothing more than that, and a couple of fully connected layers in the end. We feed this network with small patches of 64 by 64 pixels, and for each patch, our goal is to understand the camera model. We were using, by training the network with 18 possible camera models, so the output layer of the network is an 18-element fully connected network. So this CNN takes as input a 64 by 64 color image and output an 18-element vector. We feed this feature vector to another fully connected layer, or if you think about it, you might think that we are using a transfer learning starting from the pre-trained feature extractor network, and we are adding some fully connected layers at the end of that. And we ask this other network, after doing the transfer learning trick, to just output a 2-element feature vector, telling us whether that patch was meaningful or not in terms of camera model attribution. Why? Because in doing that, for each patch, we have an information whether this patch is important or not for our final decision. And we get masks like this. We have a picture, we have a reliability mask where each pixel varies from 0 to 1, so we know whether that pixel was important or not to detect the camera model with this architecture. Why? Because actually we were interested in understanding whether we could segment images somehow, and whether we could use the entire image for getting to the results or not. And apparently there are parts of the images that are really, really hard to be classified, and part of images that are not that hard to be classified. Then we merge all the information from the reliability maps and the feature extractor into another block that performs just classification. And this block provides us with the real information about the camera model. So basically we are filtering only the blocks for which the reliability masks tell us, okay, you can analyze this block and trust this block, and then we use information about those blocks to detect the camera model. And the results were pretty impressive. Here are confusion matrices obtained with 18 different camera models. On the left, if you are not using the reliability mask, and on the right, if you use the reliability mask. And actually the use of this reliability mask was improving the results a lot, because the matrix is much more diagonal. Of course, this was a work that we proposed 2-3 years ago. Now you can find other works that are performing better. If you have a look at the literature, the works that are performing at best nowadays are basically fusion of different pre-trained networks that are fine-tuned directly for this problem. So, for example, here is actually a method proposed by former colleagues of you, Anselmo Ferreira, who's working on this topic right now. And what he proposes is, okay, you can use like inception network and exception-based network to extract, to pre-process the pictures. Then you can merge the results of the two networks and train another set of layers at the end to really understand which is the camera model. And the idea of fusing multiple networks to detect the camera model Was also the idea used by the winner of the 2018 IEEE Signal Processing Cup. Actually, IEEE organized a challenge in 2018, and the goal was, given an image, understand the brand and the model that was used to show that picture, and actually the winning team used one of these methods, completely data-driven, using fusion of different networks, and that was working very, very well. Last but not the least, concerning class level 2 of device attribution, there are methods that allows you to understand which camera model was used just by analyzing metadata traces. Why? Because actually in images, but also in videos, you have a lot of header information, metadata information that come with them. Different brands and different models put different kinds of metadata. Some metadata, some header information are standard, so everyone should put those. Some metadata fields are not standard, and only some brands include those metadata fields. So by doing a statistical analysis of the metadata and the header information that you can extract from images and videos, you can kind of understand the brand and model that was used. What's the problem here? The problem is that metadata, of course, can be easily modified. So you might not want to trust the metadata that comes with your pictures, because someone might have tampered with them very, very easily. But this is not always true. Actually, there is a work that is from this year, from some colleague at the University of Florence, that rather than simply using the metadata, they were using video container information in order to understand which brand of camera was used to shoot a video. What's a video container? Actually, when you record a video, you have to save it as a video file. So you need to choose a format, and different cameras choose different format. But even if you think at MP4, which is a very common format, the way the video information is structured within the file changes a lot from brand to brand, from camera model to camera model. You can think as a file, video file as a container that is built by different elementary atoms, and if you statistically analyze, if you try learning the way these atoms are sorted, which atoms are present and which are not, which are the values in these atoms, which atoms are closer and which are more far within the stream of your video, you will actually notice that different brands organize the video in different ways within MP4 containers. And this is much harder to be modified, because if you want to modify this, you just cannot simply open the video and edit some text inside of this. You should redecode the video and re-encode it following a very strict coding architecture, but typically there are no easily usable and user-friendly tools to do so. So if you really want to change the container of a video, you can do it, but it's typically a hard job. Let's see then the last level of device attribution, and let's understand now, given a picture, we know that it comes from a camera. Now maybe we know the brand and model, but we have multiple cameras of the same model. How can we understand which specific camera is that? The idea here is that actually you can treat cameras as guns. So from police-inspired movies, and probably you know that if you have a bullet that was shot by a gun, you can try linking this bullet to the gun by analyzing the footprints that are left on the bullet by the gun itself, because the bullet turns inside the parts of the guns before being shot, and some specific traces are left there. Well, the same kind of operations applies when you shot a picture with your camera. There is one specific fingerprint that is very, very useful to attribute a picture to the specific device, and it's this so-called PRNU, the photo response non-uniformity. What is this? This is a sort of background noise that you can find on every picture that is shot with a camera, and that is very, very specific of the sensor, not just the brand of the model, but every different sensor has a different noise pattern that gets impressed as a fingerprint on your image. Why is that? Because different sensors are physically produced by machines, but the physical production of the sensor is something that is not perfect. So the machines always introduce some minor imperfections in each sensor, even if they come from the very same building block, the very same wafer of sensors. And each pixel of the sensor then responds slightly different to light. And this causes this noise in your images. This noise is not something that you can see by observing and by looking at a picture with your eyes, because it's a very, very subtle noise level that you have in there. But you can extract it with some denoising algorithm. So, how does it work? This is, I think, one of the two equations that I have in my presentation, and I also put color, so it's even easier to be digested. Let's assume, and actually this is quite true, that the blue eye is the image that you have in your hands after taking a photograph. So the image that you save on disk after taking a photograph. This can be thought as being composed by different elements. I0, the red one, being the ideal noise-free image that you would capture if there were no noise in the world, which of course doesn't exist. Then there is this term K, which is a multiplicative noise term, the green term, that is the PRNU we're interested in. That's the term that is introduced by your sensor, and then you might have some other additive, independent, additive noise, the yellow term theta at the end. So, according to this model, when you have a picture, when you shoot a picture, the blue one, you of course have information about the scene that you are capturing, the red picture, but you also are capturing the PRNU information and some other noise. If we want to understand which camera was used, we need to extract the PRNU information so that we have the fingerprint of a camera we are analyzing. How can we do that? Typically through denoising steps. So we have an image I. The first thing we do is we obtain the noise that is superimposed to the image. And hopefully this noise contains also the PRNU information, which is the green term, together maybe, with the yellow term of other noises that might be there. Of course, here I'm reporting just an example of a picture and two different kinds of noises that can be extracted from an image. What do I mean? Well, you have several denoising algorithms out there in the literature. Depending on the one you use, you obtain a different version of the noise from the image. Some might be good for you, some might be not that good. So this is one of the degree of freedom that we have when we work with PRNU. Then, let's suppose you have your camera, you have multiple images, you have multiple noise. How can you have the fingerprint? How can you extract the fingerprint from the camera? You perform a weighted average of these multiple noise that you get from multiple images. That weighted average gives you a noise pattern like this, that is the signature, the fingerprint of your device. Of course, I was telling you, depending on the denoising algorithm that you use, you might get different results. Which are two typically denoising algorithms that are used in the literature right now for this topic? Well, we have non-local mean-based denoising or CNN-based denoiser. I think everyone knows here how convolutional neural network works. You know that there are many performing denoising. There is a so-called DN, CNN, but there are also other that might be used for this topic. So neural network, you feed them with a noisy image and they simply extract the noise, maybe in a ResNet fashion. And you can use those, but a method that was used in the past, but it's still used because it's very, very effective, is to use non-local mean denoising. How does non-local mean denoising work? Well, let's suppose that you have a natural picture. Typically, you have many patterns that repeat within that picture. The idea is, if the noise on the various pixel of your image is space independent, you can try to obtain a noise-free version of your image by detecting all of patches with the same pattern from your image, realign them, and then average those. So, like in the example here, you might have several blocks highlighted in red that are very, very close. You can extract those blocks, then you can average all of those blocks together, and you obtain a sort of noise-free version that can replace those blocks. This is more or less the idea. Of course, this is not exactly how it works. Pros and cons. Actually, these non-local mean-based denoisers work very, very well for PRNU. even though they were not originally specifically designed for that. CNN denoisers apparently aren't working as well for PRNU stuff, but they're typically much faster. Because to really have a good denoised image using non-local mean denoising, well, it might take you some time, because you really need to compare lots of blocks within the image, and this is really time consuming.
The CNN-based denoising are basically like autoencoders, right?
They're typically autoencoders or UNet-like structures, which is kind of autoencoder.
So, but you still need to train them with like the different kinds of possible operations and filterings.
That's true. I mean, and they can be also trained for different noise models, because you might train them for additive noise or a multiplicative noise. PRNU itself is a multiplicative noise by definition, but additive noise, denoiser, are typically used in the literature to extract it, which is kind of strange, but it works really well. Actually, it's not completely clear to me why this really works that well, and I was also talking with other people working in the denoising field, and they had the same doubt.
Yeah, because mathematically they are quite different, but in practice you can like detect the presence of the multiplicative noise by extracting the additive noise, which is...
Exactly. And it's also true that the image model we're starting from is not the most complete image model that we have. These are sort of simplified image models, so actually there are other terms in there we might be interested in extracting or deleting. So there are lots and lots of open questions in there. Now let's suppose that you have extracted the fingerprint PRNU of a suspect camera. You have a picture and you want to try to attribute that picture to that camera, that specific device. What you do is a correlation test. You have your image, you extract the noise from that image, and you simply correlate the noise and the fingerprint that you extracted from the camera. If the correlation is higher than a given threshold, you can conclude that the picture belongs to the device, otherwise not. And there are many papers comparing different denoising techniques, comparing different devices of the same model, older models or more modern smartphones, and up to date, this pipeline is still the best working pipeline for this sort of problem. So you can find now a couple of seeding works trying to train networks to understand, typically Siamese network, to understand whether a picture and PRNU are correlating well or whether two pictures come from the same device, but they're still not working as good as the very classical model-based pipeline. Issues of this. It's time-consuming. It works very well, but it is time-consuming because the denoising costs a lot. The correlation test, if you have big images, might cost a lot as well. Memory requirements are an issue, because let's suppose you are a police investigator and you have maybe you have hundreds of suspect cameras. You need a huge database to store all of these fingerprints, but these fingerprints, despite having the resolution of an image, are not images, are not just images. You want maybe float 32 bits resolution per pixel, and it's not easy to losslessly compress them. So if you really want to store all of this information without losing information by coding them, well, you need a lot of memory.
You also have the problem of alignment, right?
You have the problem of alignment, because if you consider and resizing.
Yes. So if you rotate the image like half a degree, the image is still pretty much the same visually, but you destroy the little...
Yes, exactly. It wouldn't pass the correlation test. Yeah. That's why it might become a lot time-consuming, very time-consuming, because
you would need to try
different rotation, different flipping, different resizing, and also different shifts. It's not just a simple cross-correlation, and that's all. And you have the coding problem as well. The more you encode, the more you aggressively encode your images, with JPEG or any lossy algorithm, the more you are deleting these noise traces, which is especially a problem for videos, because videos are typically compressed with very aggressive coding schemes. And so you lose a lot of this PRNU information in videos. There are alternatives. There are faster tests. Rather than doing the correlation test, there are some tests based on random projecting PRNU in another space. There are methods to compress PRNU in order to overcome the memory requirements, but at some cost. So typically you compress the PRNU, you use less memory, but you're losing some percentage points in terms of accuracy. And there are also methods that, rather than using PRNU as a signal, they try extracting some other more features from the PRNU and then using those for classification. But still are not getting results that are as good as the very plain and old-fashioned pipeline. Just 2 words on other kind of attribution I was not dealing with the rest of the talk. I was mainly talking about cameras, but it's not only this. So just to name a few, not going into the details, there are methods concerned with printer attribution. They have been developed also here at Unica. We developed some as a collaborations, and there are also methods trying to classify smartphones from other sensors. This is something we were working on a couple of years ago. Rather than using just the cameras, we also were acquiring the recordings of signals output by the gyroscope and the accelerometers. And also gyroscopes and accelerometer had some differences in terms of noise pattern and features that could be extracted that could be used to understand which kind of smartphone you were using. As a very last thing, as the last topic of the talk, let me spend a couple of words on anonymization, because up to now we have discussed how can I understand which is the device used to acquire a picture, but sometimes this can be very dangerous. Let's consider situations in which privacy is a concern, like war photographers or countries that are not free at all and are trying to hide things from the news, but there might be people trying to shoot pictures in those countries and sharing them, and of course it would be great danger for those people to get identified because they're sharing pictures to share the truth. So in some situations we need to anonymize pictures, so that the method that I just showed you might fail, because we need to prioritize privacy and anonymization in some situation.
So you're talking about the opposite problem.
Yeah, exactly. Which from one end might be, what if I'm the bad guy and I want to be anonymous, but it can also be, we don't want good people to be detected by regimes. It's always dangerous, because when you work in forensics, you always have the anti-forensics point of view, which might be good or bad, depending on the people using it.
You need to wear both hats.
We need to have both. It's a balance.
You put both hats at the same time.
Yes, sometimes you have to.
There used to be a magazine figure, spy versus spy, black and white spy fighting each other all the time.
It's like, if you think at Star Wars, it's like the Jedi and the Sith. You're a bit of one and a bit of the other sometimes. One of the methods we recently proposed for anonymization is based on in-painting, and I think it's pretty easy to understand. What we thought is, okay, we know that there are these noise patterns that are characterizing devices. What if we destroy the picture, so that we destroy the noise patterns, and then we reconstruct the pictures from the picture itself? So, given a picture like this, what we did was, okay, let's carve a lot of holes into the pictures, and then reconstruct what was inside the holes by painting. And let's do this several times with different patterns of holes. Basically, every time that we have a picture with hole and we reconstruct the portion that we cut out of these pictures, we get some new pixels that were not there before, that have been interpolated by the others, that hopefully looks like the original pictures, but for sure we have scrambled the statistics and also the noise. So we can start from small patches that we reconstruct from the image, and then add the other patches that we reconstructed from another experiment, and then add back the other patches, and then the last patches again. And we basically reconstruct the overall picture starting from the original one, carving holes and filling the holes, and then mixing everything together. Of course, we had problems with these because the picture that we have is very blurry. So actually, if this might look nice, the actual picture that we get is the very blurry one on the top. But these can be mitigated if we use some edge compensation techniques. I'm not entering the details right now for the sake of time. But the results were pretty impressive. Actually, we could really destroy the PRNU traces by simply applying this recursive in-painting technique. A nice thing about this method is that we didn't even need to know the fingerprint of the camera that we wanted to remove. We simply had a single image and we were destroying and reconstructing that image. To conclude, as it's probably getting a bit late, what we've seen so far, that actually there are methods that can help you understanding which class of devices has been used to generate pictures, and nowadays this is particularly important for me if you're concerned with GAN-generated pictures. There are methods to understand brands and models that works very well, and for this specific problem, data-driven methods actually are working very, very well in the literature. And there are methods to understand the specific device that was used to shot a picture. In this situation, data-driven techniques are not the state of the art yet. And also, it might be important, so there are methods to anonymize the pictures as well. Of course, not everything is solved in this huge family of methods. There are many, many problems that are to be solved yet. One is the use on videos of electronic image stabilization. As Professor Anderson was mentioning before, if you work with these noise patterns, as soon as you rotate, shift, resize a picture, you are destroying these noise patterns. If you think about a video captured by a handheld device, like any smartphone that you have, those videos are typically automatically processed to remove the hand shaking motion given by your hand. So every frame of the videos is compensated, which means it's slightly rotated, shifted, resized, in order to match somehow the previous frames and remove your hand shaking. This kind of completely destroys the PRNU traces. So there are some nice works in the literature trying to recover these noise traces from motion compensated videos, but for sure there's still much work to do on this. Multi-camera devices. I was assuming up to now that we were working with a single sensor, a single device, but this is not the case anymore today. We have smartphones with 2, 3, 4, I don't even know how many cameras that smartphone has. And these are all real smartphones that are on the market. These are not just crazy computer-generated images. When you have a picture that comes out from one of these smartphones here, which sensor are you investigating? How do multiple sensors combine themselves in a single image? Well, this is something that needs to be studied from the forensic point of view. High dynamic range images. Now you can acquire HDR picture with your smartphones, but also with much better cameras, of course. How does this work? Well, let's suppose you're taking the picture in that church, so you have very bright areas and very dark areas. What you can do in order to have a very nice looking picture is you can shot different pictures at the same time, one after the other of course, but from the same position, almost the same time, and then try combining the different pictures shot with different exposures into a single picture that works, that looks very, very well. But again, you are mixing different pictures into a single one, so what happens in terms of this noise pattern that you might want to study? Well, it's not clear. Those are getting shifted, destroyed, resized, so this is something that still needs to be studied. And super resolution as well. These are pictures, these are examples coming from Google patent on one of the latest Pixel devices. They are implementing this super resolution camera app. So basically, rather than simply taking a single picture of a scene, they take multiple pictures and they combine these multiple pictures together in order to provide you with a better looking picture with less noise and with a higher resolution than the one of your sensor, which is amazing from the point of view of computational photography, but from the forensic perspective, this breaks a lot of the things that we've seen so far. With this, let me thank all of the people that contributed with their material to the talk and all of the companies from which I stole some of the pictures that I showed you today. And let me also thank you for the attention up to now. And of course, I'm here if you have any questions. Thanks a lot.
Paul, you didn't mention the problem of the dynamic focus. The new cameras that you take, and then you select the focus after you have the picture. So that one is going to be also very, very difficult.
Yeah. Because, I mean, some of this technology were already available some years ago, but they were not so widespread.
Yeah.
Whereas right now, with computational photography, you can do a lot on the smartphone and or cheap devices, so they're becoming more and more widespread. And this
look at the bright side. You have new problems to think about, so new investigations.
Yes, lots of new papers, new PhD possibilities.
Your job is guaranteed.
All right, so guys, we are open for questions, and feel free.
Sure.
Are these techniques useful for like real images that have been manipulated in parts, not all of the image, but parts of the image?
Yes. Some of these can be used. There are papers and there are like real use cases of pictures downloaded from website that could be analyzed with these methods, both related to level 2 and level 3 algorithms. So with the level 2, you can split an image into different patches and try to attribute each patch of the image to a specific camera. And so you can detect whether a portion of the image comes from one device and a portion from another one. If you move to level 3, so if you think about PRNU, you can run the correlation test locally on sliding windows. So you can detect that maybe most of the image belongs to that specific device, but part of the image is not belonging to that device at all. And so you can really draw the boundary of objects being carved in. And there are some nice examples around. They work pretty well. Given that the assumptions are strict and steady, for example, for the PRNU technique, you need to have a candidate fingerprint of a camera to make it work. So, of course, there are some assumptions, but if they hold, they work.
Or you don't need to have something, but you just need to say that they come from different devices. Right?
Yes.
More? Folks at Record, you have a bunch of questions, I know. Marcos?
Thank you for the presentation. Speaking about the device attribution problem, I was wondering if there's any method that works with more semantic features. So, for instance, if you take a picture from this room, from iPhone X, and then the algorithm tries to find whose iPhone is it. But at the end, the algorithm says, oh, it's from someone who actually doesn't study at Unicamp, for instance. So, is there any technique that combines this kind of information? The way that people, the style of posting at social media to address this problem?
I think this is very interesting nowadays because actually, to the best of my knowledge, up to now the research community is still split into different branches. Those blindly looking at these algorithms and other people, or maybe the same people, but in parallel looking at the distribution of information. But putting the two things together for sure would improve a lot, like the results. From another point of view, basically, if I understood your question, you mean, could we put some reasoning behind these algorithms? And my answer is yes, I think we should. But there are, to the best of my knowledge, there are still not specific works using these camera traces and reasoning out there. I think that Anderson might be one of the first trying these with Deja Vu projects and these very ambitious projects, because there's really a lack of this sort of techniques. But this is probably the way of doing this, especially if you want to fight fake news, news spreading that are incorrect, because you need to not just blindly use this algorithm to say, okay, this picture has been manipulated or not, but you want to understand why, by who. So reasoning might be the answer.
Yeah, just one thing. I would not try to answer why just of now, because why is way more complicated. We would need to bring like psychologists, but incorporating the semantics seems to be the trend for the next years. More questions? Antonio? No? You guys here? No questions? So Paolo, one thing that I was thinking is you presented level 1, level 2, level 3, right? It seems that all of the parts that you mentioned at the end, we would need to call them level turbo, right?
Yeah.
It's a very difficult problem. So the level that we're gonna need to attribute to them is gonna be level turbo.
Yes,
future
yes,
work.
yes,
It needs to be turbo forensics to detect those kind of things.
And the problem is that computational photography stuff are getting developed faster and faster, so it's hard to keep the pace with those.
They have the
those
industry
techniques.
in their favor, and the forensic research doesn't have the industry in their favor.
Or not yet, maybe.
Not yet.
That's why the turbo might be needed.
Yeah.
Even though their goal is not to destroy forensics.
No, their
Exactly.
goal is
Just
to
to improve
create
the quality,
nice and round
Yeah.
images.
But you pay the price, yes.
Right.
Okay.
Somehow, yes.
Tomas, do you have any other question?
No? Well, I have a slight question that it seems that you can answer. When you talk about printers or scanners, they seem to have much simpler, especially printers. Let's talk about printers, text printers. It's very common you have to identify a document where it was printed. Do you also apply this kind of techniques, or they can be much simpler? Because the kind of image is much simpler.
I wouldn't say much simpler, because one of the issue is that printers evolve in time much faster. Like you change the toner, you're changing lots of information. The printer itself degrades in time. So maybe you have lots of data of that printer, but it's not so coherent with the new data of the same printer. For sure there are traces left by the printers in terms of mechanical traces left on the paper, how the ink or the toner gets imprinted on the paper, but I wouldn't call them easy. Another thing is that one of the ways of dealing with printers with these sorts of techniques is to focus on some letters. So, like I had an example here. This is the pipeline of one technique focusing on the printed letter E. So it depends then how many E you have on the document, and you might need to specialize a method for different letters. I mean, it's not the only solution, of course, but it might be very, very tricky.
That reminds me, you probably never saw a typewriter, but that's how it works. When you want to identify a typewriter, you would look at a certain letter and, each type was slightly off or something.
We developed work together, and some things that are not present in images, in digital images, that complicate things for printers is that, first of all, in printers you have like the connection of digital and analog, which for images, cameras, you don't. So you have something that's on a paper, that's analog, and then you need to transform it into digital, and then you need to analyze a trace left in the analog world and not in the digital world. Sure. So this is one of the complications. The other is I don't know if I told you, there was a paper that we wrote, and the reviewer asked, okay, I'm convinced that your technique is good for white papers. Now I want to see what happens with yellow, red, and green. So we came back to the lab, and okay, let's collect some colored papers now. Let's print them, and let's see what happens. And it seems that the method was okay for these different colors. But when you change its parameter, like from 75 to 90, the algorithm was broken because it was the texture of the paper was different.
Okay.
So in the printer, you have like the analog playing an important role that in the digital you don't have.
And probably also the scanner plays a role.
And the scanner. So the place that you put the printed document in the scanner, on the scanner,
Okay.
on the plate, also differs.
Yeah.
Because look, you have the analog.
Yeah, each spot has a
Document?
different problem. Yeah.
But the interesting thing is you have the analog document that you want to look for telltales, but then you put on the scanner, right? Which is going to capture the acquisition telltales of the scanner. So now you need to tell apart the acquisition telltales of the scanner and of the printer. So it's interesting as well. But we have a technique that it's around 95%.
It was just a curiosity. I was thinking about the old typewriters. So.
But the motivation is exactly the one that
Sure.
you mentioned. Analyze the letters like with a loop and see what happens.
Okay.
Anything else? No?
Yes, please.
Just one curiosity for the problem of the anonymization.
Anonymization.
They also commit this style of photo response non-uniformity that has each sensor just to show who was taking this picture.
It depends. The inpainting based method that I was showing, for that case you don't need to know which is the peer review pattern of the specific camera you want to anonymize, but there are other methods. Actually, I skipped that slide, but another technique that we developed was a neural network that took as input an image and a very specific peer review, and that network was trying to remove that specific peer review from the image. So for this method to work,
We can add another peer review from another camera.
and you can also add other peer reviews from other cameras. There are techniques to do that. Actually, if you do that, it's not that easy because you need to balance very well the power of the peer review that you're injecting. So there are some tests that you can do on an image to understand whether the peer review that you're extracting is the natural peer review or it's an injected peer review.
So somebody had to take a picture from our way and they see it from neck and that.
Yeah, you can try removing the peer review of the camera you used and inject the peer review of another one and try to make another one responsible of those pictures. There are techniques to do that.
Or you can take a picture. You can take a picture of the screen, and this is gonna be.
Take a picture again.
No, you just have the digital image, and then you take a picture
Of the
of a
picture.
screen.
Yeah.
Then you have now the telltales of the camera
Yes,
of the
they
new
also
picture.
use how is a camera. You choose and you pick the photo from the guy and the computer vision recognition from detect the photo of this guy. I think this guy is something like that.
Yeah.
I have a question. It's about the games.
Mhm.
How do you fight an enemy that can learn anything that you bring to the place?
It's a nice question,
Yeah.
but I would just change. GANs cannot learn anything.
No?
They always will leave some traces that you can also learn.
Yeah, I mean, that was the rationale behind the method that we started working on. If we, rather than modeling the GAN, we try modeling what is not a GAN, what is a natural process, this is probably an easier way of fighting GANs. Because in the end, GANs still apply some mathematical operation and some algorithms from your data. So in the end, the picture that you get will suffer from some interpolation artifacts. The pixels of the picture will be somehow correlated in between them because they come from filters that have been learned. Of course, it's not easy to spot again. But I think it's not that easy to completely generate something that absolutely looks as a natural picture. And the other thing is, from my point of view, GANs needs a lot of data to learn. So even if we develop a forensic algorithm, they might learn how to fight that specific method, but maybe for some algorithms it's not that easy to generate quickly such a huge amount of data for them to be learned. And also if we insert things that cannot be backpropagated in the algorithm that we develop, maybe for GAN it's not that easy to understand how to fight those techniques. So I think there are few weapons that we can use against GANs. It's something that we're going to find out, I hope, in the near future, but let's see.
Anybody else? No? Paolo, thank you very much, and I
Thank
hope
you
to
for
see
inviting me.
you and Simone here other times.
Sure.
Thank you.
Apologizing because he needed to go. And he asked if you're going to share this slide. So you can send to me and I can share. Thank you. See you in 30 minutes.
What did I miss? Ciao Paolo. I just arrived here, so and nobody told me about this presentation. So what it was about?
Camera model identification. The different levels.
Please send me this presentation.
Okay. But I think you are.